Hi, Lexi. How are you?
Doing good, Joe. How are you doing?
Doing fantastic. So this is our second attempt at trying a podcast. We had a bit of a technical difficulty last time, but I have high hopes for this. So
Yeah, me too. Fingers crossed.
yes, exactly. For people who don't know who you are, do you want to give a quick intro?
Yeah, for sure. I'll give a quick intro. I was thinking, sort of reflecting, I've given a million different iterations of this elevator pitch, and I feel like the long
Okay.
and short of it is just I'm somebody that goes where I find interesting problems. And I think that a lot of that started out in maybe like 2010, 2011, when I found a mentor in machine learning that I got to do some research under. I think you know him as well, Richard
Yep.
Wellman.
Yep.
And at the time, machine learning was a little bit more oriented around this sort of functional analysis approach than I think it is today. But
Hmm.
that was really interesting just because it has some really solid generalizable mathematical underpinnings. So that kind of piqued my interest in sort of the overlap of machine learning and math. And at the time, I was also working in sort of a lab doing statistics in sort of this laboratory oncology setting. So I got to help out a little bit with experimental design and statistical analysis. And that really refined kind of my statistical understanding of machine learning and science. But then I got really interested in this sort of more symbolic way of looking at things. And
Hmm.
that led me into logic, which was ultimately what I ended up studying when I did my PhD in math. By the time I exited that, there were much bigger computers for much cheaper. And so, machine learning was kind of hopping off in a really exciting way. And I decided to go back that direction and sort of started down the data science road, which was a little bit of a newer, rapidly popularizing field at the time. Started a little small consulting firm, and have just been, in this space. Utah's a great place to be doing data.
It
So,
is. It is. Yeah. I think I first met you. I was working with Dr. Wellman on a very early machine learning startup back in the day. This was in circa 2012. So I crashed his class and he kept mentioning there's a really smart student named Lexi. It's like, well, if you're calling her smart, she must be brilliant. So I guess when we first met each other, however briefly that was, and years
you
later,
were in a,
here we
you were
are.
in a good few classes. I remember you.
Yeah. Yeah. I had to go hang out at his office afterward. So get
Oh yeah, that was when the real work got done.
yeah, exactly. So, but those are fun times. I think it was machine learning, as you point out. It was, I think it was a much different field. Uh, it was still based on trees. Support vector machines were still sort of the rage. I think
Oh yeah.
neural nets were. Deep learning was sort of, I think, just on the up and up around that time, but it really, I know that Wellman felt that, yeah, they're kind of black boxes and probably not the best approach. So, but here we
Yeah,
are.
I mean,
Deep learning took over the world too. So,
yeah, well, I think that, when you've got bigger, stronger computers, you don't really have to have the same degree of artistry. It's a kind of
no,
controversial thing to say. But, and in defense of support vector machines, I
they're
think that
great.
there is this like, right, of course, I have to just in honor of Wellman. But, there's this theorem that basically says that any neural net can be represented through a support
Yeah,
vector machine with some very specific kernel. So, mathematically, I think it's a more general framework.
yeah.
Computationally and practically speaking, especially as you scale up on, these sort of parallel processing frameworks, that's not, maybe the tool you'd want to go with for
Yeah, they're kind of
implementation.
they're kind of hogs on resources from what I
Oh
remember.
yeah,
So,
absolutely. They just don't scale in the same way. Not right
nah,
now.
not right now, but you never know. I think the
You
interesting
never
thread
know.
in machine learning is what's old is new again. So, and I get that sense right now with, generative AI is sort of, I think, for better or for worse, becomes synonymous with AI. But you're starting to see, I think, more symbolic approaches coming back into the fold, and which we can probably touch on in a bit. But yeah,
Oh
it's
yeah.
all these techniques. They have a way of overlapping with each other. I think I even remember seeing a paper where support vector machines may have held some promise with transformer models in terms of making it more efficient. So yeah, it's interesting.
Oh, I mean, and that's the kind of cool thing is once you develop the general underpinnings, you can just kind of mix and match, right? So
Yeah.
I want to say that like the core of machine learning, and this might be controversial, has been the same for decades, but there's been like really interesting development, and iteration on that theme,
Oh yeah.
variations on theme, right?
So, but you took a detour. I mean, it's pretty interesting. So you took a detour. You also got your PhD in logic, right?
But it's fair to call it a detour.
Okay.
I do think that logic was more in line with that kind of symbolic approach to AI. And I do think that informs the way I approach semantics. So that might be something we end up talking about, but a detour in terms of the depth that I went for my dissertation, but certainly spiritually aligned with things that are, practical in today's data world.
What was your dissertation on?
Oh, that's a whole can of worms. But I think that, okay, brief detour. Apologies to the audience. So my dissertation was sort of around this space of the undecidable in math. A lot of people think that everything in math is true or false, right? But the fact of the matter is a bunch of mathematicians got together at the turn of the century and sort of hammered out what are the axioms of mathematics, because we'd all been doing this quasi-formalistic activity for a while, but it became apparent that we really needed to formalize this into a symbolic language that eventually something like computers could parse through, right? Without having to have any sort of external reference to what's a set, what's infinity. We just wanted there to be a string of symbols. Is this a valid proof? Under these rules, is the theorem correct? That was the goal. And in formalizing that, we came up with this axiomatization that was just like 8 rules for all of math. And I think for a while it was thought that now that we've got these rules hashed out, we can just sort of systematically churn through them to derive all possible mathematical truths. And, in the 30s, Gödel found out that that's not really the case. So there's this distance between the syntactic and the mathematical and the semantical sense of mathematical truth, where the uncertain or undecidable lies. And so my dissertation research was really in finding techniques to move between different universes of mathematics in which certain statements were true in one and false in the other. So, you could use that to construct universes in which your proposition held, and also use that to identify what statements might be undecidable from your beginning axioms. So it was really this exercise in that space between, what is the meaning of math? What is its interpretation in the context of a different universe of objects? And what are the symbols that, you use to derive proof and mathematical truth from?
For the audience, what would be an example of this?
Yeah, okay. So I think the most famous example is the continuum hypothesis, right? You have the natural numbers. Let's just call it 0, 1, 2, 3, 4, etc. Your integers. And then you have the real numbers, right? So the stuff you do calculus on, as many decimal points as you'd like. And the question of the continuum hypothesis, so first off, those things are different sizes of infinity. Really cool proof. It's got this neat diagonalization methodology. Cantor actually was sort of pushed out of the mathematical community after finding this result, because it was just seen as so outrageous that you could have different sizes of infinity at the time.
Yeah.
But it happens. We eventually came around, a little too late for Cantor, unfortunately. But those two sets of numbers have different sizes of infinity. And the continuum hypothesis basically asks, is there any size of infinity between the size of the naturals and the size of the reals?
Mm.
And turns out that's not actually answerable by those axioms of mathematics itself. The answer lies outside of it. It has to do with what you believe the world of mathematical objects to be, because we know what rules those objects have to follow. We decided on the rules. We don't know what the entire space of all of those mathematical objects look like. And whether a set of the right size of infinity exists or not can't be derived from the rules itself.
That's an interesting paradox. So
it is. And I think that there have been a couple times in the history of math where we've come up with a statement that we're like, oh, we should be able to solve this.
yeah.
People poke at it for decades. And then eventually somebody's just like, can't solve it. And we all have this big existential crisis over like, what are we doing here? And then we just like forget about it. and move on. So I think that the undecidable is a little bit of a taboo in the mathematical community from what I found.
Yeah.
When I used to tell people in math what I did, they were just like, ugh. But I think everybody respects the
Oh, that's
reality.
funny.
It's just it's an existential threat to the way they think of the work they do.
Oh, for sure. And I think I broke my brain when I first learned about different types of infinity when I was doing my math degree. Yeah, my brain
Like,
was
don't get me drunk
fried.
at parties. I will absolutely walk through the diagonalization proof.
Actually, that sounds kind of fun. We should totally do that sometime.
Let's do it. No, let's do it.
Yeah, yeah. For the audience, we both live in Salt Lake City, so the chance of this happening is actually pretty good.
Oh yeah,
So that'd be a fun
I'm counting
party.
on it.
Yeah, really nerdy party, but pretty fun. I'll have to invite Matt Housley, my
Oh,
business partner
please.
of ours. Yeah, he's also a math PhD.
This is sweet. I like it,
Yeah.
kind of like show and tell. Everybody will have to bring something to just sort of blow minds.
I'll just bring a bag of chips. I don't really have much to offer to this conversation, but
That's super cool too.
or booze. I can help you guys along. So that's interesting. And I mean, so given your background, especially the nature of your dissertation, do you find any um, overlap with what's happening with machine learning today?
I definitely do. I mean, like I was saying, I feel like just the whole flavor of the logical approach lends itself a little bit more to this symbolic approach to AI.
Mm,
I think independent of that, there's two dimensions. There's sort of this symbolic way of looking at things, which I definitely want to go deeper on. But then I
yeah.
also really wanted to just briefly touch on this other phenomenon, which is really around understanding the assumptions that you make. And I feel like because I worked in a field where the assumptions were everything, and we were going all the way down to the foundational level and then trying to kind of like break stuff or find the things that weren't, decided by those assumptions. When I approach a data science problem, that's always where I go to. It's not what model should I use for this problem. It's what assumptions can I make about the space that I'm working in, the thing that I'm trying to solve. And then from that, you sort of construct the approach. So I think that the spirit of that is very much embedded in the way that I approach data problems.
Interesting. Can you elaborate more on that? Like what?
Yeah, for sure. So I feel like, if you take I didn't take data science classes. They didn't exist when I was in school,
They
right?
did not exist.
They really
I can
didn't.
argue you actually took better ones because you took hardcore math classes. So
Right.
yeah.
Those were the data science
Yeah.
classes at the time, with a little bit of a caveat, which is that I feel like data science engages a little bit more with that sort of pragmatic, engineering-y, epistemal, like a inductive kind of reasoning, whereas mathematics is like almost purely deductive reasoning, right? And it's a little bit in a vacuum. So I would say mathematics is like at the core of data science, but there's also like this other set of tools that you need to be able to use as a data scientist that mathematicians sort of traditionally haven't quite grabbed a firm hold of.
Right.
So, I think that, like we were saying at the time, data science classes didn't really exist, but it's all math. And the way you do math is you say, let such and such be the case. Let such and such have these properties. Does it have these properties? Is it the case? We don't know. We don't care, right? But if you assume that, then this and this and this follow. And I think that when you approach a data science problem, a lot of times as you're trying to get your feet under you, you know what the goal is, but you don't know how to get there. And so if you can start by just like, well, what if this was true? What if this was true? What if this was true? Then can I come up with a solution? A lot of times you can then manipulate the data or restrict the data in such a way that that assumption holds, and then you can carry it through to your conclusion. Whereas I feel like the approach I see a lot more often is I'm going to just Google like how to do a classification problem or how to do like a clustering, algorithm, and just like pop whatever shows up in there. Do I care about what assumptions that algorithm is based off of?
Yeah.
Depending on how good of a data scientist you are, maybe not. I think, if you, well, and also how much time you have, right? So
that's a big thing in business, actually. Yeah, it turns out.
Yeah. Well, and it's interesting that you mentioned that because I've also heard, so naively, when I first went into data science, my thought of how I would know if something was actually true, if I'd actually come up with a model that described reality, was I'll just take two separate modeling approaches to this problem. And if they converge on the same answer, despite making different assumptions, then I know I'm probably on the right track, right? They're converging to reality. That's not something that's a practical approach in business, right? You can barely get enough time to implement one solution, let alone like multiple models to triangulate against. But I do think that it points to sort of this more solid underlying epistemological observation, which is that something which is true or something which is a valid model, which will be robust, is one which makes minimal assumptions or which still operates more independent of the assumptions that you're making, right? And I think that we see that a lot when people will like launch a model to production and it immediately breaks, right? Like the accuracy just tanks. You made some assumption that may have been true of your training data that was not true of the way that you were generating your production data in the case of machine learning. So this is a really pervasive thing that comes up. I think we're just not quite getting to like, why is this happening? And it's that you need to really think critically about the assumptions that you're making before you dive into a problem.
I mean, how do you determine the assumptions for a data science problem? I think that in my experience, there's a problem you're trying to solve, and I'm talking about in a business context. You're a data scientist working in the business, so to speak. There's the assumptions that you have, there's the tools you have, and there's the constraints that you have. But there's also other factors, like the goals you're trying to drive towards for the business, and so on, which I found sometimes is at odds with um, maybe taking, I guess maybe having, well, one, having the time to come up with the right assumptions,
Right.
And diving into a problem. And two, I think, as you point out, the constraints of time and so forth. Like how do you balance like coming up with, I'd say, like really great assumptions and testing those versus the constraints of the business environment you operate in?
I'm really glad you asked, because I feel like that's the next level of maturity for a data scientist is, okay, you know how to sort of identify these assumptions in a vacuum about the problem. But, if that assumption breaks, let's say, then there's a certain degree of risk posed to the business, right? There's risk posed to the accuracy of the model, but depending on the context in which the model is being used, maybe a false positive and a false negative have sort of a different cost to the business. And so I think that understanding the risk exposure in terms of the models that you're using relative to the risk appetite and the values of the business is where the magic really happens. So you have to be able to translate between what is the degree of risk and error that I'm taking on in taking this particular modeling approach, given the underlying data, and what is the business's appetite or capacity for absorbing that risk should, the assumption break.
That's really wise. That's really wise.
It's hard to do. It's hard to, well, and I think that, it requires you to be able to navigate just like the pure mathematics and logic of the situation, as well as the kind of psychological elements of the situation, which is really where those questions of, risk arise, because there may be risk associated with business goals, but there may also be risk that's borne by very particular business stakeholders just because of their sort of political positioning within the company.
Sure.
And I think that, that's something you have to be aware of as well, and be willing to sort of talk openly with your stakeholders about, what the risks might mean for them in specific.
Yeah, definitely. Kind of back to the data scientist then. I mean, so you run a data team, and how do you view mentorship and education for your team? Like, what are the things that you would prioritize more for people in your team versus I don't know, anything else? Like, what if you were to list like a top 3 things that you sort of overweight on for competencies and skills for your team, what would those be?
For sure. Well, I think it's easy to start with a good team. And I know that's easy to say.
It's really easy to say.
It's so easy to say. But I think if you start with people who are really curious and driven and are willing to kind of poke and prod at something until they figure out how it works, you're in a completely different situation than if you're not dealing with that. I find that I just can't work as well with team members that don't have that natural and innate sense of curiosity. And I think that most data leaders would probably say the same thing. I think it's one of the most important qualities a data scientist or a data professional can bring to the table. I think in some ways you have to be operating kind of like a detective, right? As a data scientist, you have to want to poke and prod until you understand like why this is breaking or why this isn't working or what this is trying to do. But I think that beyond that, what I see my role as a leader being primarily is facilitating connection between the data team and business stakeholders, engineers, people a little bit more on the operational side, so that they can start to form their own picture of the landscape of risk and opportunity. And beyond that, I think that questions about how to level up technically, these kind of debates about what should our tech stack look like, or what tools should we be using, those all really become secondary.
That's really interesting. What do you, I guess when you talk to data scientists, what's the feedback that you get? Like, what do you think that they are interested in learning?
I work with a very specific kind of data scientist and data engineers, right? Like I said, I think they tend to be a little bit more naturally curious than, and I've worked with the spectrum, right? So
sure.
I've worked with the broad spectrum, but I think it's really important to curate the right team. That's so foundational. But I think that what I feel most from them is actually a desire to understand the business side of things more. Like that's one of the most consistent things that I hear is I want to understand the motivations. I want visibility into why we're doing this. I want, who should I talk to better understand XYZ? And then I'll set up that conversation. I'll get that dialogue flowing. And I find that that's often where the most productive conversations happen with the data team. And it's what I hear them asking for most often. Outside of your standard stuff, like, of course, can we spend a little bit more time paying down tech debt and data governance and stuff? But, for the most part,
people want that.
Oh, people, and it's important. It's super important, right? But I think that, on the data governance piece, just as an example, you can't do data governance if you don't know what people are doing with the data, right? That has to come first.
It helps.
It helps.
But these are the things too that you're not taught in most data science curriculum, right? I think that the way I see it taught, at least, it's it's very tactical too. Like the things you mentioned, I'm trying to wrap my head around it, because it's like you're talking about very almost strategically focused data scientists in a way, where they're continuously learning, focusing on understanding the business and the problems, and applying data science to solve those problems. But the way data science is taught, I think, is very interesting, because it runs counter to that, right? Like you're taught in a very tactical way, like here's Python, here's how you can use pandas, here's scikit-learn.
Here's k-means clustering. Here's logistic regression.
Exactly. Yeah. Like your 80-20 splits and all this other fun stuff, and cross-validation, which is all super important stuff. But so when I see data science graduates coming out, it's like they're super eager to apply all these machine learning techniques they learned. Like if you tell them to go do, to go analyze data set, they'll kind of look at you strange and say, well, that's not machine learning.
Oh, totally.
I can remember one interview I was doing with somebody. I asked, it was kind of a trick question to kind of diagnose this, but like basically, you're given a table of data. How would you analyze this and quote cluster? This was a trigger word that I left it intentionally there. And so the person's like, oh, I'd obviously use k-means. And I was like, yeah, but like a group by could do that too. In SQL. So, so it was more of a diagnostic test. But
I don't know if I've gone on my k-means like Google Cloud documentation rant for you.
Please, let's do this. I've not heard you rant about this.
This is a little specific, right? But I was going through the documentation I can't even remember what it was. I don't know if they still have it. But basically documentation on GCP for sort of this inbuilt k-means clustering algorithm. And like the default initialization for the number of clusters was log n, where n is the number of rows, which doesn't make any sense to me, right? The number of clusters should have nothing to do with the number of rows. And then because that could blow up so wildly, they're just like, cap it at 10. So the default parameterization was like log n for the number of rows capped at
or 10.
An upper limit of 10 clusters, which just has like no possible plausible interpretation mathematically or semantically as to why that would be a valid parameterization to start.
That's
It's
hilarious.
kind
I
of what we're
had no
talking
idea about
about,
that.
right? So I
Yeah.
don't know what's going on there, but to your point about sort of the data science classes, I feel like this might be sort of an extension of the same problem somehow. You learn all of these tools, but you don't know how they work. You might kind of snooze through the class. Maybe the professor like walks through 5 minutes, a couple pictures of like, this is what k-means clustering is doing. But could you really come away from that and say like, if you were in an accident and retained only sort of the foundational memories of like how things symbolically behave, but didn't know what anything was like what anything was named, couldn't Google it.
Yeah.
Would you be able to put back together what a k-means cluster does if you were asked to like do this kind of problem? And I think you should. I think you should be able to have any understanding or knowledge of what the names of any of these models are or the heuristics for how they're used completely wiped from your brain and be able to derive it in the same day, because it's a very straightforward idea that follows naturally from the shape of the problem.
Yeah. Well, the shape of the problem is a very, I think, astute description too, because every problem has a different shape.
Yeah.
I don't know if this goes back to your dissertation or not. Um,
Well, it also goes down back to like the functional analysis foundations of machine learning. Like it's the
yeah.
literal shape of the problem, right? And you embed it in this, maybe you embed it implicitly in some altered kernel space or use some other inner product, but the shape is everything. That's how machine learning works, sort of at its core foundations.
I think that's literally how it works. Yeah.
Yeah, it's literally the shape.
What do you wish that what do you wish would be brought back to machine learning?
Creativity, critical thinking. I know that there's a lot of people out there that are still going hard on that route. I don't want to say like it's disappeared, but I don't know. I feel like it became easy to feel like you were doing machine learning, but not actually engage with what machine learning is. So I think thinking back again to how a lot of these classes are often taught, you'll be given some pristine tabular data set where everything's scaled and clean and you've only selected the columns and variables that make sense for the particular decision problem. And then you're like, oh, I'm going to do machine learning on this. And you just like try a bunch of different, off the shelf models and you parameterize and you're like, I'm, a machine learning pro. Well, getting that data set like was the machine learning problem. Like that is
Yeah.
most of the work that you will do. And you won't get exposure to that. You won't get exposure to like what, throwing open the door to just the unmitigated chaos of a legacy data warehouse and trying to extract something meaningful for the decision that you're trying to make. If you're just handed this perfect tabular data set and an output variable and told predict this.
Yeah. I think I became acutely aware of this when Dr. Wellman and I were working at our machine learning shop. So for the audience, I believe it was one of the first, if not the first, automated ML companies in the world.
Yeah.
And so, then the notion was give us a tabular data set and we'll give you predictions, right? Maybe it's classification, maybe it's numerical output, whatever. But I realized from that experience that the algorithms, although interesting and obviously very complex, I mean, Richard had developed an entire ensemble learning, method in his spare time, which is kind of interesting on its own. But the underlying data sets that we'd be getting, it's like that's where the fun starts. I think because there were no clean data sets, and in a lot of cases, we'd be getting data sets that I would say had very little signal at all. And here we are trying to find you know, I can't, I think because of disclosure, I can't name exactly what we're doing, but like, you know, like let's say we're going to try and come up with a classification for some really rare event, for example, right? But the data set itself um, is incredibly sparse and doesn't, the data set itself doesn't actually lead to any conclusions about said event. So, you know, I think as we started digging through this data set, it was like, yeah, uh, your hyperplane was you'd almost be trying to overfit to find signal in it
For
because
sure.
you couldn't. So that was a really early indication. And then, you know, I took it upon myself just to go and say, screw it. If you're spending all this time building data sets, let's figure out a way to at least like automate the feature engineering for 90% of this workload. So
Yeah.
that's, you know, I kind of cut my teeth on, that's I think where I started deviating more towards data engineering and ML engineering, just precisely because that, in my opinion, was actually the bigger problem, was just getting the data set to begin with. You
I
know,
mean, that makes a ton of sense as a natural transition. And it actually, you know, it brings up a good point, which is that a lot of times the data engineers are doing the work that the data scientists probably should have been involved in picking apart, right? And
yeah.
so you have these two different people who are making assumptions about the semantics of the situation that in a lot of cases aren't talking very closely. So, you know, you'll make a certain set of assumptions and just like throw it over the fence. Then we'll make a certain set of assumptions and throw it over the fence to the business stakeholders. And I feel like that's a really common thing that, again, like to go back to your question of what can you do as a data leader to help your data teams, it's break those barriers, like talk to people,
Yeah.
because that's the only way to preserve that continuity of meaning through the process and make sure that it shows up in the data.
Oh, for sure. In fact, I was just writing about this afternoon. You know, as I'm writing, as we're speaking right now, I'm finishing up chapter 4 of my book on data modeling. But you know, as I started writing on a framework for data modeling, it was the 5 Ws of journalism, and but the two that I put at the top was actually why and who. It's not what the data itself,
Right.
you know, or like where is it located and how, you know, what are we going to use to solve this problem, but it's who and why. And who I actually put at the top because you need to actually talk to people and understand what it is they're trying to do and get that nuance. You know, they're the domain experts, you aren't. And I think the mistake I realized with auto ML is that you're blindly trying to apply you know, a brute force mathematical technique to something that implicitly requires domain expertise.
Right.
It
And
doesn't
I
work.
think, right.
Or
Or it
you
needs
need
to be,
both. You need both.
yeah,
Yeah.
exactly. It needs to be further parameterized. And I think we were talking about this a little while ago, where you have this more symbolic approach to machine learning, you have this more statistical approach to machine learning,
Yeah.
and the sort of the tides of what's in oscillate. But I do think that you need both. And I've heard some really bad takes on this around like,
Oh,
oh, one's discrete and one's continuous, so like they can't play together. That there's like a million and
what
one
does that
ways.
even mean?
I don't know, Joe.
Okay.
I couldn't even possibly begin to pick it apart because like you do it in math all the time in a million different, you know, permutations. So I don't buy that. I think these approaches need to play together. And
Yeah.
I think that these more statistical approaches, right, that you find more commonly in auto ML can be really strongly informed by a more symbolic approach. And I think
Yeah.
we had talked a little bit about like, you know, expert systems AIs used to be a thing that people associated with AI. Like,
Yep.
but now I even talk to, I wouldn't say data professionals, like people who are kind of proximal to the space. And they're like, oh, that's not AI. And I'm like, no, like that's been AI for a long
Yeah.
time. It's just, you know, what AI is shifts significantly
Oh,
over
it
time. And
does.
it has to do with branding more than
Oh, it totally
technology.
does. It totally does. I mean, you know, we've met when Richard and I working together. We've refused to use the term AI because it was so out of fashion. Because there was
Right.
this, you know, because neural net sort of polluted the space with a few failures that had happened. So, you know, we called it a predictive analytics and then machine learning, right? But like AI used to be the thing, and then you're absolutely right that that name goes, and now it's back with a vengeance. It's like
Oh,
shit,
yeah.
linear regression is probably AI at this point.
Oh, it
You know,
is. No, it is. I mean,
yeah,
of course, linear regression is AI. Like if, and I think that that's like, I don't want to say that, but I kind of do, right? Just because
yeah,
the point is there's not a clear delineating boundary. I mean, if linear regression is finding a decision function with some inbuilt error function, and then like machine learning is like basically that, but a different kind of decision function or a different kind of error function, I just don't see how you can justify that being the dividing line. And of course, out there in, the broader discourse, nobody's talking about like the cost error function, as being the definition of machine learning. And I think that, or definition of AI.
Yeah.
And so I think that for people who really understand the core of it, it's kind of all AI. And for people who are just sort of riding the trend, it's whatever the big thing is at that given point in time.
Yeah, 'cause I think it goes back to Thomas Mitchell's description of a machine learning, I think it was, which is something learns from experience E with a bunch of other stuff, right? So you could apply linear regression to make a machine learning model under that context, and then it's machine learning, right? But
Well,
you
and
could also
that's a
use
good
it as
point.
you could also be a statistical
Right.
approach, which isn't machine learning at all. It's just like
Right.
you get a number and away you go. So
No, that's a good point. I mean, it's not so much about the tool itself, it's about the context in which it's being used.
yeah,
Right.
yeah. And AI is definitely one of those things where it I mean, I think we're in a fascinating point in the data and AI and machine learning space right now, precisely because there's so much attention on it. Part of me feels icky about it in the sense where when I walk around conferences, I see a lot of vendors pitching quote AI products. Uh, but I don't blame them; they have to. It's sort of this prisoner's dilemma, or if you aren't, then you look sort of old-fashioned, like you're
Oh,
out
totally.
selling carriages. Uh, but I wrote an article about it today, F around and find out, I think was the title of it, which was more just a kind of I think just a buyer beware article to
Right.
customers that are getting bombarded by vendor pitches about quote AI products, because I think the crux of it really is the underlying data sets of a lot of companies are still in shambles. And so in the latest rage right now is throwing like Texas SQL on top of everything. But my whole argument is like, if the underlying data sets are crap, I mean, do you really think like throwing Texas SQL and that's a good
I
idea?
mean, don't even get me started on this generic BI space. Like
Oh dear.
that's not, yeah.
No,
I mean,
okay.
maybe
Oh,
let's do go there,
let's go
right? I
there.
know,
Why not?
yeah,
I
let's go
love
there.
let's go unhinged Lexi. Here we go. Um, what are your thoughts? What's
I mean, I know we've had I know these discussions have been brought up in the context of like what's a semantic layer, which also I've got to take a brief detour here. I was reading through one of your articles where it mentions like I asked a bunch of people, and some people were like Kimball is data modeling, and some people were like set theory and predicate logic, which as a logician is just a crazy thing to say that's data modeling. Like I'm
that
here
comes
to
to
say that makes no sense.
that comes from the relational data model, folks. Yep.
Well, but I
Yeah.
think it's like saying that cooking is molecules, right? Like
Exactly.
kind of in a way, but like no, like not in any sensical way, right? Not in any way that gets to like a real salient description of what's going on. But I think that, I think that there's this idea that, again, just like in math, we thought that the structure of the symbols contained the meaning or could embody the meaning. And we found that it couldn't. There's a gap there. And these BI tools operate on the assumption that the structure of the thing illuminates the meaning. And that's, I think, just not how meaning works. There is something outside that, something that must be connected. To your point about the AutoML, right? Like there's subject matter expertise that has to be brought to bear on the problem somehow. And I think that even outside of this data modeling conversation, I kind of wonder if these more symbolic approaches are becoming more popular because LLMs kind of need to be guided in the same way with this external structure that illuminates some of the, the relations of meaning in a way that this more, Markovian underlying process doesn't.
Yeah.
Or the
It seems to be the
statistical underlying
case,
process.
right? Like I got some friends working on, interesting research around incorporating knowledge graphs into, LLMs and semantic layers. And, then what Microsoft just came out with a paper on GraphRag a couple of weeks ago that looked pretty cool. So it's sort of that intersection of the old and the new. I mean,
Yeah.
graphs have been around for ages. So
I mean, I think that there's an opportunity in all of this to really like mush these things together in a way that propels us forward.
yeah,
Right. And I
agreed.
think that these these debates, like it's this, miss the point. It's like, okay, it's got to be something new.
Yep.
What's that new going to look like? How do we navigate the space of acknowledging that there's two sides of these coins that need to communicate with each other?
Mm-hmm. But I think it's an argument that a lot of people don't want to explore because it feels like orthodoxy is more comforting in some ways.
I'm sure it is. Like everything's
Yeah.
definable, right? I mean, it's the same reason the mathematicians didn't want to talk to me about the undecidable. It's epistemologically uncomfortable, but like we need to evolve in our epistemic understanding. You're telling me we're still operating under the same epistemological framework that we inherited like during the Enlightenment era? That's wild. I can't believe we're still allowing ourselves to toil under that burden. And I think that, you know, I see this a lot too. I've got some friends that are in, you know, in medicine and even just trying to unravel, you know, what's the randomized controlled trial? What are its, you know, assumptive underpinnings? How do we evolve beyond that as we gather and analyze data in new ways and new technologies and methods emerge? I think that the fundamental underlying problem is we don't have the epistemological foundations. We have not gone deep enough to say what we're really doing, because there was this picture of science that, again, very Enlightenment era. There's this like turn of the century deductive mathematical framework that we're operating under. And we kind of oscillate between the two and the tools that we use and the way that we think. But we haven't come up with anything that really merges them. It's sort of like the physicists with, you know, the grand unified theory. Like, what's our grand unified theory of what we're doing with respect to data and meaning? They're incommensurable, the two epistemological frameworks that we're working under right now.
Yeah, and I think the operating environment we're in too, it's simply a matter of throwing more GPUs at the problem if you're in machine learning, right? So,
true.
you know, so it's like I don't need to think about it. I just need more horsepower.
Right.
And more electricity and so forth. So that's the other crux. Is
but
like,
I mean, you see a lot of companies digging a hole for themselves in that way, because it's just like, okay, well, just, you know, we're not going to spend the time to sort of rethink our approach to this problem. We're just going to throw more compute at it. And when they get the bill back, it's just like, whoa, what is this? Well, that's, you know, just throwing more horsepower at it.
Yeah, it's interesting. Because it feels like with large language models too, you know, I talked to, you know, pretty big AI experts, I suppose. And the interesting thing is they're trying to like prod and poke at these things too. It's almost like some alien being had landed on Earth and you're attempting to figure out how to talk to it and reason with it and figure out its boundaries and its shape. You know, sort of the you know, the blind man and the elephant. You know, the old tale, but because yeah, I mean, even people I have been in the space for a very long time, and I would say help shape the space, the machine learning space. They still have some confusion about you know, exactly what the hell is this thing. So.
Oh yeah, absolutely. You know, I think the best take I've seen on LLMs actually came from an anthropologist, Harari. He wrote *Sapiens*.
Yeah.
But I think he made this observation that a lot of the power of the LLMs are really them tapping into the topology of language.
Yeah.
Right. So you have this natural shape of language as it clusters, as the culture has sort of borne it out through, you know, many iterations of meaning to different people. And you're just tapping into that topology and writing the currents of sort of like the waves as they flow through that, you know, that landscape. And I think that there's something to that. I wish that there was more of an attempt to uncover what we can learn about that semantic landscape through the technology of AI, you know, acknowledging, or LLMs, acknowledging that that's not the whole story, right? But then we use that as an opportunity to explore what is the nature of that gap. But I think that these deeper questions aren't really being entertained because we're like in this strange sort of schizophrenic state where we want to derive value from these AI models, right? And that's almost always going to be in a very specific business use case, but also like the hype machine turns on this dream of like Gen AI. And we can't like really engage these deeper philosophical questions because at the end of the day, like somebody's going to come knocking, asking like, where's my ROI on this thing? And that's going to have to do with something much more specific than like how navel gazily your LLM is.
Oh yeah, and I mean, so I speak around the world at some big conferences, and it's interesting how much AI has captured the public's attention, right? So I specifically like I've given a couple talks at different conferences in the Middle East, and these are very well attended conferences, like hundreds of thousands of people show up, and the only thing people want to talk about is AI. It's AI this, AI that, and if you were to like just walk around and you didn't know any better, you'd think like the second coming of the Terminator is happening or something, or I don't know what positive AI counterpart that is, but I don't know, Dolly or
No,
something.
totally.
But you get the idea. So or her or whatever. But it's like but everyone has this impression that the world's suddenly gonna be all these like flying cars and
Oh, totally.
AI doing everything, and but you talk to people on the ground who are actually in charge of like getting this stuff done, and they're like, I have no idea what the hell to do. It's crazy.
Right.
So, but it's fascinating because if you didn't know any better, you think that AI, it's just right around the corner. Like, we'll have AGI just like tomorrow, right? I mean, I had Roman Yablonsky on the show a few months ago. He was he's an AI safety researcher, and he's convinced that even the current iteration of ChatGPT has capability of becoming super general intelligence. I don't know. I don't know what's in this model. Maybe it is, but his whole thing is like we're all dead soon anyway. And I was like, cool. So why don't you go party or something and go live it up? Because like we're all gonna be gone anyway. So it's just yeah, these are things that go around my head. It's like, you just see all these different perspectives, but then you talk to people who are actually in the world doing the stuff. You're like, it's not as easy as it
I think that's
sounds.
always the case, though. Like I think back to when I worked in laboratory oncology setting, and because I had come from this space where there were like much younger, pluckier undergraduates that are like, science is everything. Like, science will deliver us and tell us everything about the universe, and not that it isn't a really indispensable tool, but you talk to the scientists and there's like, I don't know, bud, like just like you got to turn 3 times counterclockwise before you start the centrifuge, or it doesn't work. I don't know what to tell you. And so I think that there are always that's always the cultural disconnect between the mythology of the thing and the practice of the thing itself. And
Yeah,
I find that, I find that conversation around AGI to be really interesting, because I kind of think that our Western individualist isolatory mindset has perfused itself into the way that we talk about intelligence, that it could be a thing in isolation. It could be a thing independent of the language and the culture and the input and the values that feed it, right? That you could just be like a brain in a vacuum and have ideas and navigate through it and be creative. And I just don't know that that's the case, right? I think there's this much more integrative sense in which consciousness arises that, from just the strictly data point of view, comes down to what is the data that you're feeding it. We all know this implicitly. We
yeah.
all know that the data matters, that the data is like the whole story. So why is that not part of the conversation around AGI? What does the data hold in it? What is that topology? How do you navigate through it? What is what are the heuristics through which we as humans are sort of navigating through this space of meaning?
That's 1,000%. And I always seem like the boring old bastard on stage when I'm talking about data and
I
why
believe
why
that.
why it's important and why you need to build a foundation and stuff. I feel like I'm teaching, I'm telling people they should, eat 3 square meals a day, get your protein.
Oh, totally.
People are just like, yeah, that's cool. No. So
But that's the thing that will be true 30, 40, 50 years from now, right? Like,
yeah,
smoke 3 cigarettes a day to improve your health had a very short lifespan overall in terms of medical advice, right? And I think that you're out there preaching the truth. It may not be the sexiest thing at this point in time, but it's not going to change. Like, the data matters. You've, you know, meaning has to be somewhat extrinsic to the symbolic and statistical process. Uh, these are basic facts. And I think we
yeah.
talked about this a little bit even before machine learning was a part of the conversation. There was this whole like revolution in this debate about scientific language and logical positivism and
Mm,
what is the nature of language and consciousness. Do sort of the symbols that our language operate in relation to things in the same way that like the underlying objects in reality do. And I think that the end result of that is that it's not that simplistic, right? There's a couple different ways to look at it that, again, we haven't really brought, and I don't expect it to be fully resolved. Like, I don't expect us to have the grand unified theory of everything. And if I can take a little bit of a detour on why I don't think that, there was a really interesting conversation between Einstein and Gödel, who were actually very close friends. Gödel being the one that had the, his famous incompleteness result about sort of that gap. And Einstein being a really true believer in like the grand unified theory. And Gödel's point was, if it's not true in math, if you can always have sort of something beyond, always have these, gaps that you fall into, and then you try to close the gaps and it opens up new ones, why would you possibly think that there could be sort of a complete and consistent theory that describes the universe? And I think that's the case with meaning. So, I think the goal is not to come up with something that contains all of meaning. I don't actually think that's logically possible from a formalistic point of view. But I think we can do better as practitioners in finding ways to actually navigate and talk about this process together. We're falling short in engaging those real questions about how we practice data science, how we do machine learning.
Well, I think you're thinking about data science at a much deeper level than I think is normally discussed too. So
I think you have to.
Yeah,
I mean,
I agree.
The whole point of data, what's data, right? I saw that. I thought it was a really good question. Whatever it is, it's partial. It's partial and has some relationship to an external world. And the manner of that partiality is, it gets skimmed over, in pretty much every conversation that I've had with data professionals and business professionals across the board. I think there's a tendency to be like, well, this is the data we have. Let's just go ahead and use it. I'm like, yes, that's true. But you have to understand first, what is the relationship between that partial subset of data and the world that you're trying to reflect on the outside? You can't just feed this kind of distorted subset of data through some off-the-shelf model and expect that to reflect the world outside.
You can't? I'm kidding.
You can't. That'd be nice, right? It'd be really nice.
That would be pretty sick. At that point, I think you would actually have had AGI doing your work for you.
A long time ago.
Yeah, that'd be dope.
Yeah, well,
we're not there.
No, well, and I mean, that's even a really interesting question, because is one of the fundamental functionalities of consciousness its partiality, that it has this attention capability that sees certain things and doesn't see certain things based on sort of the semantic system and the value system that it's operating under? I would argue yes. And I would argue that maybe one of the shortcomings in AGI currently is just there's not really that attention framework that is linked to the underlying notion of semantics. So something that I would like to poke around in, because I think that could be really well mathematically formalized if we spent the time. But that's the cool thing about math, is that it like hooks up to both the philosophical side of the questions and the sort of computational implementation. And that's where the power is. It can make that whole journey.
Oh, it's literally the bridge between the two. I mean, that's
exactly.
Yeah, it makes me want to get back into math again. I'd have to start with remembering addition, but that'd be fun.
You know what? You'll pick it up so quick. I felt like when I was teaching every year before classes started, I was just flipping through the books. Like, how does this work again? So it comes back.
No, it comes back like a bike. It's funny. I was going through my old storage container, and I had I think 1,000 books that I collected and read over the years. I haven't touched them in like 10 years, but one of them, it was funny, like life insurance mathematics, because I was studying being an actuary. Yeah, and it's like flipping through that, and it started coming back, and I was like, damn, these are pretty intricate formulas that you use to calculate mortalities. Yeah. So.
Oh yeah. Well, and I think that one of the interesting things about reading that is not so much like, oh, I'm totally going to need this mortality formula. It's just like, okay, like how did they come up with this in the context of the shape of their problem? And it's funny, you see economists do this all the time. They'll have like, oh, this is the law of the market, blah, blah, blah. And it's like, no, it's just a derivative, right? Like, I get that the context was the big thing. That's what the law is, right? But at the end of the day, you just described this thing with the function and this thing with the function, and you took a derivative. But that's cool, right? Because that's where most of the problem is. And so I think that it's, when you understand that these laws don't just come out of thin air, they're fundamentally mathematical in nature, then you know how to translate between these kind of fuzzier philosophical notions of like, this is a thing, and something that can be like implemented and calculated off of and eventually embedded into a really robust piece of technology.
For sure. I think you got to understand the limitations of these things too, though, against the data sets in the real world and against the reality of the real world, right? So econometrics is one of those things where I feel like
Yeah,
there's a lot of
absolutely.
physics envy, as they call it. And sometimes the formulas blow up because the world is an extremely dynamic system that simple models can't account for. Just
That's why I don't go in with a model in mind. I go in and
yeah,
look at the data and then come up with an equation that'll work in that.
smart.
Like it is always more time saving to just create the equation or the model from scratch than it is to try to retrofit some of these textbook equations onto your particular data set for exactly the reason you described.
I just wish that was taught more often, especially in data science, because right now here's the algorithms, go find a data set,
Right.
throw them at it, throw all of them at it actually, and do a tournament of best
Right.
fit and see what works, right?
See
Instead
what
of,
does best. It's
yeah,
kind of the exact opposite approach, like literally
yeah,
the
it is
exact
the exact
opposite
opposite.
approach. And it's wild
Yep.
how that happened.
Yeah, it is. Kind of
Sad.
closing out, anything that you're excited about coming up in the next year or so? What do
I'm
you
excited to see. Yeah.
excited to see
I
what?
mean, I'm excited to see how this conversation evolves. I feel like people are getting mad at each other, which is always a really exciting time intellectually, because it means that, different kind of paradigms are brushing up against each other. And I just hope we lean into that and kind of, take the opportunity to build a more solid, a solid underpinning for what we're trying to do here in data. And I think in science and technology more broadly.
Hmm. Yeah, I think it's a fascinating time in the industry. I don't think I've
Oh, yeah.
seen it like this. Even during the deep learning days, which was several
Right.
years ago. But yeah, it's fascinating. So anyway, Lexi, thanks for the fun chat. I'm glad it finally worked out.
Oh, yeah.
For people who want to learn more about you, how can they do that?
I'm on LinkedIn. Go ahead and find me there. Always happy to chat about this stuff. I mean, I definitely open invitation if you've got thoughts about, semantics and some of what we talked about here in the data or AI space.
Yeah, I need to introduce you to some of my semantic nerd friends. So I think you would have
Oh,
a
I would love that because I come at it from a completely different angle, right? So I think there's a bunch of different fields that have just sort of converged on this. And I think it's always nice when we get to kind of swap notes.
oh yeah, absolutely. Cool. All right. Well, have a good one, and
Awesome. Well, thanks so
we'll see
much,
you at a
Joe.
fun party where we can talk about infinity. So,
Oh, yeah. No, I'm not going to let that one drop.
okay, sounds good. All right, bye.
All right.